Hi, I'm Melissa Hartwig, and I'm going to be doing Trench 8.6, number 5, letters A and D on convolution theorem. The convolution theorem states that the Laplace transform of f convoluted with g is equal to the Laplace transform of f of t times the Laplace transform of g of t, which is equal to big F of s times big G of s. Letter A, we are evaluating the integral 0 to t of t minus tau to the 7th, tau to the 8th dt. We should recognize that this is equal to f convoluted with g, where our f of t is equal to, this is f, and this is g, t to the 7th, sorry, it was a terrible 7, and g of t is equal to t to the 8th. So we'll take the Laplace transform of t to the 7th times the Laplace transform of t to the 8th, which is going to be 7 factorial over t, oops, that should be an s, over s to the 8th, sorry, times 8 factorial over s to the 9th. And when you combine these, you're going to have 7 factorial times 8 factorial over s to the 17th. I left the factorials in because it's just a really big number. What we need to do now is we need to try and figure out what the t equation is for this. And so the first thing I'm going to do is I'm going to take out the 7 factorial times 8 factorial because that's a constant. And this is going to give us the Laplace inverse of 1 over s to the 17th. Now this is pretty close to something that we would recognize the Laplace inverse of, except for one little problem. We need a 16 factorial up here, and so we'll have to divide by a 16 factorial out here. And then what we have is 7 factorial times 8 factorial divided by 16 factorial times t to the 16th. So that one was pretty easy, pretty straightforward. Now I'm going to do one that's a little bit more complicated, which is letter D. And letter D is the integral from 0 to t, e to the minus tau, sine of t minus tau, d tau. Now again, we should recognize this as being f convoluted with g, where this is our f, this is our g. Our f of t is going to then be equal to sine of t, and our g of t is going to be equal e to the minus t. So now we'll do our Laplace transform of sine of t times the Laplace transform of e to the minus t, which we should know is going to equal 1 over s squared plus 1 times 1 over s plus 1, which will equal 1 over s plus 1 times s squared plus 1. Now to solve this, we're going to need to use partial fraction decomposition. So we know that this is going to equal a over s plus 1 plus bs plus c over s squared plus 1. So 1 is equal to a times s squared plus 1 plus bs plus c times s plus 1. And so we'll start out by letting s equal minus 1 because that will clear out both b and c. So 1 is equal to 2a because minus 1 squared is 1, 1 plus 1 is 2. And so that leads us to an easy a is equal to 1/2. Now we're going to let s equals 0, which will clear out our b. So we will have that 1 is equal to a plus c, which then leads us to c equaling 1 minus a, which of course is equal to 1 minus 1/2. And so c also equals 1/2. Now we have our a and our c values. Now we will let s equal 1. So then we have 1 is equal to 2a plus 2b plus 2c. Oh, I ran into my other box. Excuse me. Which we can then say is equal to 1 plus 2b plus 1, because a and c are both 1/2. 1/2 times 2 is 1. And this, of course, will equal 2 plus 2b. And then solving for b, we will get minus 1 is equal to 2b. And so b is equal to minus 1/2. So now we have a, b, and c. We can go ahead and plug them back in over here so that we have 1/2 over s plus 1 plus minus 1/2 s plus 1/2 over s squared plus 1, which of course will equal 1/2 over s plus 1 minus 1/2 over s squared plus 1 plus 1/2 over s squared plus 1. Now taking the inverses of all of these, we will have 1/2 the Laplace inverse of 1 over s plus 1 minus 1/2 times the Laplace inverse of 1 over s squared plus 1. Oh, no, I'm sorry. There should be an s here. So this is s over s squared plus 1 plus the Laplace inverse. Oh, nope. Plus, forgot my 1/2 there. 1/2 of the Laplace inverse 1 over s squared plus 1. All of these are Laplaces that we should recognize, so that we end up with 1/2 e to the minus t minus 1/2 cosine t plus 1/2 sine of t. And that is a much easier way of evaluating this integral than doing our standard integral evaluation would have been using convolution theorem.